Good morning. My name is James Little, and my company is Mass Spec Interpretation Services. Today I would like to share with you a free training video on creating and using retention indices in the NIST software. This video and associated resources, plus many other training videos, can be found on my personal website, A Little Mass Spec and Sailing. Retention indices can be used in combination with mass spectrometry data to provide nearly unambiguous identification of isomers. This is a very difficult task to accomplish with EI mass spec data alone, but NIST offers an extensive list of resources including RIs for greater than 139K compounds, RI and mass spec data for greater than 114,000 compounds, and associated GC methods and RI citations for over 400,000 literature references. AMDIS is used to determine the RIs for compounds in the GCMS analysis, and the results are sent to the NIST search for evaluation. This tutorial assumes that the user is familiar with the content in parts 1 and 3 of a previous series that I did on the NIST Mass Spec software. These tutorials can be found on my personal website, A Little Mass Spec and Sailing. Here's a slide that shows the overview of the process for determining the retention index of a compound. First, the user must run the sample in a C8 through C40 straight chain standard mixture using the same GCMS conditions used for the analyte. Then AMDIS interpolates between the standards to determine the analyte's RI. And the RI of a straight chain hydrocarbon is defined as its carbon number times 100. So you can see below on the top we have the total ion chromatogram for the C8 through C40 straight chain hydrocarbon mix, with the C8 all the way to the left, the C40 all the way to the right. And in between we're trying to interpolate to determine the RI of the analyte between the C17 and C18 to determine that it was 1765.7. You'll note on the side over here the baseline rises. That's just due to an artifact in the analysis. I really stopped the analysis here on the temperature program because there was no useful data here, but the data system just kind of fills that in as a straight line. Here I have plotted the retention index versus the GCMS retention time for the C8 through C40 standard. As you'll note below, the slope of the curve changes during the column temperature program. Therefore, it is very important to bracket the analyte between the two standard peaks for AMDIS to interpolate. You can see below that we were trying to interpolate between the C17 and C18 to determine the analyte, but you can note that the curve does change slope in this area versus the middle area versus the top, again showing the importance of bracketing. The GC temperature program is shown to the right of the slide. AMDIS uses a CSL file for the standard C8 to C35 hydrocarbons to automatically create a calibration file .cal. This CSL file contains an EI spectrum of each hydrocarbon to locate the position of the peaks. However, the higher molecular weight hydrocarbon peaks tend to broaden at the end of the GCMS analysis, and due to this broadening and the lack of a reliable signal for the molecular ion intensity for many of these species, it hinders their automatic detection and calibration. Thus, it's much easier in most cases just to add the C36 to the C40 RIs and associated retention times manually to calibrate, as we'll show in the example today. You can see below how narrow the peaks are in the earlier part of the chromatogram, but as it goes to higher and higher temperature, the peaks tend to broaden, making it much more difficult to do it automatically by the program. Here's an example of a typical CSL file. These files can be viewed and edited with the Notepad utility within Windows. I have supplied C7 through 35 and 8 through 35 CSL files in a resort zip file on my website. Thus, there's really no need for the user to create their own. The example below shows for the first record of the 27 records present in the C8 through C35 file. The key points are, it's got a name that I assigned when I created it. Also entered this defined RI value for a hydrocarbon, 800, 8. This is C8, so 8 times 100 gives you that value, 800. The value of 1 in this file indicates that it will be used in the calibration process. This other field here that talks about the mass to charge being 114 for this must be found at greater than 0.1% in the calibration process for the entry to be calibrated. And below is a table of the mass to charge intensities. Below is an example of a typical calibration file after AMDIS did its automatic calibration. Only values in the first two columns are important, the GCMS retention time and the RI for the hydrocarbon. Of course, there are 27 entries that were determined automatically in this file for the C8 through C35 species. You can see the one at the top is for the C8 and the one at the bottom is for the C35, again showing their retention time in the first column and their retention index defined in the second column. Here we have an example of a typical calibration file that we've added values manually to. We've added the C36 through C40 RIs and associated retention times. And we've also added some user comments to the left of the retention time and RIs. So below you can see where I've added 36, 37, 38, 39, and 40 hydrocarbons, and of course these are their retention indexes as defined, the retention times here. And over here, these values really don't matter anything to the process, so I just deleted those out and put a comment that said that I'd added these values manually so I would remember later when looking at this curve which ones had been changed. I will now demonstrate the software. The first thing I'll do is recreate one of the slides that I showed you earlier, so I'll open the file that I wanted to use and I'll go to the data and find it. It's in this file. I'll find the hydrocarbon mixture and open it first, C7 through C40. We have that on the display on the top. Now for comparison, I will go open in here. I want to open in the active window so I can compare them, and I'll open the analyte file. What I want to do is to make the time scales the same. It makes the complete run here in the top and the bottom, but I want to make them match up, so I have to go to View and say Same Time Scale. I'll also stretch it out here to get past the solvent in the file. And now we have the view as we were shown before. We have the C8 here on the left all the way to the C40. We have our analyte that falls somewhere between the 17 and 18th, C17 and C18 hydrocarbons here. And you'll notice there's a little artifact here, as I noted before. That's because there was no need to run the analyte all the way to the end. So we stopped the temperature program here and stopped the file to save some time. But it gives this artifact here where it just shows a raise in the baseline. Now to do the actual calibration, we really don't need this file here that shows the analyte. So I'll left click on it to select the box. You can see it highlighted it and say File at the bottom here and say Close. Now we only have our calibration file on it. The C8 actually starts here. The mix has a C7 in it, but it kind of comes up with the solvent, so we're not going to try to calibrate in that area. We only want to calibrate from C8 all the way out to C40. So to do that, we have to go into the top menu here and say Analyze, and pull down and say Analyze GCMS Data. Now normally when you come here, you'll probably find it in simple mode, because that's the way that you normally process things in AMDIS. And that when you get through doing this calibration process and doing some of your normal work, you might need to go back there. So remember this, to go back to simple here when you get through if you no longer need the RI type data. But for the RI calibration, we'll come down to where it says RI Calibration Performance. All right, we have to tell it which library we want. So we have to go find it. So I'm going to click on here to go find my library. And I'm going to say Select New. So you have to know where it's located at. Mine are located in this file here called Sandy's RI Data. And I'll come down till I find the C8 through C35. This does have C7, but it came with the solvents and it might not be properly resolved. So I'm only going to do C8 through C35. So I'll pick it and say open. And then say, after I've get that, I've got what I want now. It's a CSL file. I say save. Now all I have to do is run it. So we'll run it here because we've got our right file in here, and we'll calibrate. It's going to warn us that it's going to overwrite some things. That's okay. One other thing that I need to do, I want to go and change where I put the file. That's one thing I need to do. So I'm going to go down to this tab before I do it and create a place to put it that I know where it's at. I'll say select new. And I need to go down here and say it is a cal file. Look at the bottom right corner here. I need to say whatever I want to call it. And what we're going to call it is C8 through C40.cal. And say open. Okay, it'll create it because it didn't exist. So I'll just go back. Now I've got everything I want. So I said save. So I have my file that I want to process. I want to calibrate. I have to use this option, and that's where I want to save it. And I'll say run now. When I do that, it says it's going to overwrite or create this new file, and I'll say okay. Okay, everything went real well. You can see they put T's above everything that were calibrated. So that was over here. If you come over the information box on the side, you'll see C8. And I think that view, you have to show the window that you want. But I think it's show windows. We're showing all the windows, component profiles and everything. So that's windows being shown there. So that's good. And we'll go over and click the next one. And you could go through all of them. That's the C9. And the last one it did was the C35. It did not do our 36, 37 through 40, again, because that's not in the CSL library that it's searching for the spectra for. So we pretty much have our calibration now, the automatic part of the calibration. Just a few more comments about the automatic versus the manual calibration. As I said before, the T's up here indicated all the targets were found all the way out to the C35. But when you go 36, 37, 38, 39, 40, the peaks just tend to get broader. And it just makes it harder for the automatic calibration to work. Sometimes I could get the higher ones to work out toward 38, but then it would mess up some of the lower ones. So I found it better just to chop it off here at the 35 and do these manually. And it's just very hard for the software to do it because you can see the peaks here became broader, much broader than the ones over at 17 minutes, the ones over at 27 minutes at the longer retention times. And the other things, if you look at the molecular, the spectrum, I'm going to click on the C8 here. You can see it has a good molecular ion at 114 for that species. But as you get out to these, the molecular ion gets smaller and smaller, and it gets very difficult for the software to decide if it's the correct component and label it correctly. So thus, it's just better to do these manually. Now I have to go and do the manual part of the calibration. You can see it stopped at C35 here. If you click on that one, you can see it was at, that's the last one it calibrated. So that's my 35 right there. And you go over the information, you can see C35. The next one, I'll just click on the little down box at the top here, the little arrow going down, and that'll tell me the retention time of the top of that peak. And you can see it's 25.687 minutes right here at the bottom. And I do this for all four of those. I write them down on a piece of paper so I can manually add them to the table. And I do it all the way through 40, taking those retention times. Now after I've got the retention times written down on a piece of paper, I minimize this window and I go find the file. You can see I went to open the directory I stored it in. It was C8 through C40.cal. And you can see that it stopped at 3500, which is the last, that's a C35 hydrocarbon. So what I need to do is manually add those 36 through 40 that I've added. So I'll just say File, Save As, and I'll just save it as the manual add file. I'll go and say All Files. So I've already created this file in the past, so I didn't want to take the time to manually type everything in for you. So I already had one called C8 through C40 manual add. So I would have just saved as that to get that file. And then after I get that file, I'd close this one, leave it alone, and go back and find the one that I did the save as. And in the example, it would have stopped here. What I've shown is after I added it in, I didn't want to take the time to type in these while you watched. So I typed in 25.687 off my piece of paper, and that has to be 3600 because the 36 hydrocarbon in the mix, and 38, 39, 40. And like I said, these columns here really don't matter for the calibration, so I just went ahead and added C36 added manually just to remind me that I had saved these. So now I have a calibration file that's calibrated all the way from the C8 all the way to the C40, and I would just say File, Save. I want to check and see if the calibration was done properly, so I'll go back and open up AMDIS, go back to my Analyze up here at the top, click on Analyze GCMS data. But here, I don't want to do the type of analysis I did before, so I want to pick, instead of before I was doing this RI calibration performance, that's how you calibrate, but now I need to switch to use retention index data, so it'll use the calibration that I just performed. I'll have to go down and tell it where that calibration data is, so I'll click on the little box here on the left. It'll let me select New. I have to make sure I know where it was. I put it in Sandy's RI data, and here's the one I created. This is the one that I manually add. I open it, and then I say Save. And you can see now that I've got what I want. I've got my data file that I want to calibrate using my new calibration file, and I've got this file that I added, and now all I have to do is say Run, and it does it. So let's go check now. We'll go out and click on the little down arrow up here at the top, all the way to the right at the top, and click on it and go down to the information box here, and it shows that the RI for that is 3,999.6, pretty close to 4,000, isn't it? And just check all four of those. That one's 3,900, that one's 3,800 essentially, that one's essentially 3,700, this one's essentially 3,600, and the last one should be dead on because it was done by the auto calibration, 3,500. So now we've checked that the calibration worked, and it worked on our file, so it's good to try it on the analytes that we want to analyze. So now we need to go open our analyte file. So I'll come up to the top here where it says File, and I'll say Open. And these are a group of analyte files, but this is the one that I showed originally. So I'll open it and say Open. It's asking me if I want to delete what I had before, and I'm fine, I'm through with it, so I'll just say Delete. And now I have my analyte that I had before. What we need to do first is make sure all the analysis parameters are set right. So I'll go to Analyze GCMS data again. That is the file that I want to do. This is the calibration. This add cal is the one I want to use. So I just say Run. When I get through, you'll see if I click on the red arrow up here, you can see over in the right side is determined the RI for this compound. It's 1765.7. Now we're ready to send the analytes RI over to the NIST search. So we come to the bottom and we click on the window, go to NIST library, scroll over to Go to NIST MS program, and it'll automatically do the search. So at the top we have our unknown, or our compound of interest. You can see it brought in the retention index of 1765.7 that we determined in the AMDIS program. And on the bottom we can see that the best hit, if we come over here to the hit list, is the compound of interest. This is the structure for it. I've already added this to a library, so you can see it did match the 1765.7 that was in the library that it added previously. It's got some of the column conditions. You'll also note if you come over here to the best hits again and come over to the second hit and look at it, it's actually from a specialty library here, a different library, and they had the retention index in there as 1766. So it's very close to the one that I thought, 1765.7, which is interesting. The other thing that I wanted to note, let's come down to the 6th hit here and go over to the window and look at it. I just want to show you the other type of information that's in the main library. It'll have the retention index for some values out of the literature and how they were determined, name of the article, etc. So there's a lot of information about retention indices from the literature in the NIST software as shown in their library for the main library. So that pretty much demonstrates the whole process. So let's go back to the PowerPoint to discuss a few other things. The experimental. All the example files that I've used that you might want to do to try to reproduce this with your computer are on my website in a zip file named resources.zip. That's in a little mass spec and sailing website. The experimental for the C8 through the C40 is found in the file C7 through C40.d. If you look under the ACQ METH text file, you'll find the column, the injection port temperatures, volumes, etc. that you need if you wanted to reproduce a similar experiment on your GCMS system. The C70 through C7 through C40 standard is available from Signal Aldrich with this part number that you can buy. And after the acknowledgments, I'll demonstrate how you can form your own CSL library. However, as I stated before, you can just use mine. In the resources.zip file are included a CSL file for C8 through C35 and C7 through 35. I didn't use the C735 example in my work because the C7 was not resolved in the standards from the solvent file or the solvents that were present in the sample, so you really couldn't use it to calibrate. So I started with 8 and went to 40 and did not do 7. There'll be a lot of useful things on my website, and the useful links I have put below. This is actually part of the handout, and the links will be active in the handout on the website. Parts 1 through 5 of the NIST search software course will be very useful. The AMDIS manual, if you start reading on page 29, section 2.9, there's a lot of information on how to use retention indices and to calibrate in there also. The NIST manual has a lot of information about retention index or retention indices in the document. You just need to search for it using the search command. Also, I'd like to acknowledge all the help I had from NIST. I had to learn how to use this, and I didn't know a whole lot when I started, but by talking to all of the people below, I found out what I needed to know to produce this video, and I hope you'll find the video useful. As I mentioned before, I'll show you how to make your own CSL library. In most cases, the ones that I've given to you within the resources.zip folder or file will be adequate for all the needs that you would have for doing retention index determinations with AMDIS. However, there might be some special applications, so I'll pretty much show you how I made my CSL files when I started. So I came up here to File, and I'll open the data file that I wanted to do, and I'll go find the one for our C7 through C40 calibration mix. We'll open it, and here we go. Here's the raw data. We'll need to go up to Analyze and go to Analyze GCMS data. As I said before, a lot of times we'll be using these other functions like retention index data, RI calibration performance, but when you do the basic processing, you want simple. And I'll run it. When I run it, I essentially get pure spectra for all the components. It's deconvoluted them from the background and marked them. To see where they're marked, you go to this top arrow, you click on it till you get on the one you want, and I want to get on the C8 hydrocarbon, the first one in the mix that I'm interested in adding to my CSL library. And you can see down in the bottom right corner, it weighs 114, so that's the one I want. Now I go up to Library, Build One Library. The first thing I need to do is to tell it where I want the library to be. So I go to Files and I say Create a New Library. I'm still going to put it in this, I'll just put it in this AMDIS 32. Doesn't really matter where, but that's where it's going to go. You just got to know where you put it so you can retrieve it if you need to put it somewhere else. I tend to try to put libraries in the files in special folders where I'll be working on a project, but we'll just call this test 3 will be the name of this library. A very important part of this process, it always brings up the target library as MSL. That's not going to work. We have to change this with the pull down menu to CSL. So remember, it's always come up MSL. If it's going to create a CSL, you have to tell it to do a CSL. So now I have the CSL to create, and I say, and I know where I want to put it, and I say OK. Now you'll see that where it will be stored, and it'll be called test3.csl. So what I do is I've selected this component here at retention time 1.4871, and I'll just add it to the list. So I've added it to the list that I want to create this CSL file. The next thing I need to do is to edit it. So let's just call it a C8 because that's the C8 hydrocarbon. Let's get rid of this chemical ID. It doesn't really mean anything. And it's got the retention time right. And of course, since this is a standard of the C8 straight chain, its RI will be its chain length times 100. So we put in 800. So that's good. And say save. We need to say use for RI calibration. And if you'll remember the RI calibration file that I showed you earlier in the PowerPoints, it'll put RI equal 1, which means it will be used in the automatic calibration. RI is 800 carried over from where we put it in the last window. The other thing that I want is require a peak. And I'm going to put in the molecular ion, 114. I want to make sure it's the right species, so I want to make sure it has a molecular ion and a minimum abundance of 0.1 or greater, and say OK. And now we've got our first entry. We can go and get us another entry. So let's go and get the C9. The next peak is at 2.563 minutes, and let's add it. Let's edit it. Name it C9. Get rid of this chemical ID and say the retention indices. You can go down here, 128 is the molecular ion down here in the right hand corner, and then the spectrum. Multiply it times, this is C9, so 9 times 100 would be 900 is the retention index, and say save. Again, we'll go require a peak, but here we, of course, we have to put in 128 molecular ion down here in the right corner, and require minimum abundance and say OK. And that's what I essentially did for the C8 through the C35 when I created my CSL file, and I just had to step through each one manually and add them to the file. And you can see this is something you don't want to do very often, so just either do it yourself the first time or just use my files. I have the C7 through the C35 and I have the C8 through the C35, and of course you'll always have to add the C36 through C40 manually. So that's pretty much the process, and when you exit this, you'd be able to go find that file and open it up in Notepad and look at it, edit it if you needed to do some more editing, and make sure it's okay. So that's pretty much the whole process, and so I hope you found this video useful and can apply it in your work. Good day.